A vector has, Pauline, we need you. A vector has
direction and magnitude.
right, that's straight from
oh yeah.
Despicable Me. Right, two?
No, one.
First one.
The first one.
All right. Sorry, I don't know if you watch cartoons with kiddos, but that's it. That's right. Magnitude and direction. That's what a vector is, right? It's a length in a direction. All right, and we usually represent them with I and J, don't we? I means straight sideways. J means straight up and down. We break a vector into straight, because they're usually diagonal, headed off in some direction diagonally. So we break them into I and J, straight sideways, straight up and down. Okay. So with that in mind, now we're going to, and so we have these new things called vectors, which are direction and magnitude. And now we're going to, we learned to add them last time. How do you add two vectors? How do you multiply a number times a vector? Now today we want to learn how to multiply two vectors, at least one way. There's another way if you go higher in math and calc 2, but for now we'll start with the easy way, and that's called the dot product. See, that's the name of our section. The dot product means multiply, doesn't it? The product of two numbers is the multiplication of those numbers. So dot product is the multiplying of two vectors.
What would we use this application for? Or is that a whole other subject?
Oh no, that's today.
Okay.
Today we will.
By the end of the lesson, it'll give us like a
exactly
real
within an hour. I think we'll be there.
Okay.
Yeah, yeah. All right. Yeah, because they're just making stuff up here, aren't they? Right? Math is just made up. So they made up this thing called the dot product. Okay, it's how you multiply two vectors. So let me write out vector v. Here's vector v. If you wanted to draw a vector v, could you draw it? What does a 10i mean?
Over 10
Yeah,
to the right.
10 to the right, right? The I is sideways, the J is up, down, right? So that'd be over 10. And what's the number in front of the J there? I don't see any number. 1. So it'd be over 10. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up 1. Boom. There would be vector v, right? It's over 10, up 1, isn't it? Good. At vector w, what's he look like? Over 1, up 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. Over 1, up 10. There's vector. I didn't do that too neatly. But anyway, there's vector w. So I want to get something in front of your eyes. So we got vector v, vector w, and we want to multiply them. That's kind of weird. How do you take a couple of arrows and multiply them? That's what a vector is. How do you multiply a couple of arrows? We actually learned how to add two arrows and subtract two arrows. You just do it component by component, right? If I wanted to take vector v, 10i plus j, and add vector w, I plus 10j, right? If we wanted to add two vectors, we did that last week. You just add the I with the I and the j with the j. It'd end up just being 11i and 11j, wouldn't it? That's how you add them. But today we want to multiply them using something called the dot product. So, how do we do it? Let's say it was up to you to make this stuff up. Let's see how you think compared to how the people that made this up think. If you were to take vector v, which is 10, I assume none of you have actually seen this before, and dot product, I plus 2, that's v dot, you put a big old dot in the center, dot product. So vector v dotted with vector w, how would you do it? What would you say? You just had to make something up.
I would think foil.
Yeah, foil seems, that's what I would think too, what Benjamin said. Wouldn't you think it's naturally just foil it out? Turns out that's not what they did. But that's how I would think naturally too. I would just think, well, okay, you want me to multiply those? Wouldn't you just take this one and go to both, and then this one and go to both, right? Turns out they didn't do that. Why? Well, they didn't want an IJ mix. You see what would happen there? I would get 10I, what's an IJ? I don't know. They didn't do that. But that seems very natural to me too. That's what I would naturally think. So I want you to see. Why am I doing this weird thing? I want you to see that what they made up is just that. It's something they made up. It's not like something that had to be that way. You get the idea of how math works? They literally make it up. They go, hey, this is how we're going to multiply things. But they make it up in a way. Now, why do they make it up that way? Because it turns out to be useful that way for some real life things, which we'll see within the hour, or maybe an hour from now. Anyway, and you know there's a second way to multiply two vectors. Oh, I already said that, didn't I? In Calc 2, there's another way called the cross product. It's a whole different thing. So my point is, they're making up ways to do these things because these ways will turn out useful. So they said they didn't go with the FOIL thing. Instead, what they ended up doing is they said, hey, let's just multiply the I number with the I number and drop the I's. And then we'll multiply the J number with the J number and drop the J's. And then just add up those numbers, and that'll be it. That's called the dot product. It's actually easier than FOIL. You don't have to do all four multiplications. You just have to do the front times the front. So what number's in front of this? It's a 1 there, huh? So 10 times 1. No I. I dropped off the I's. I just took the I number times the I number, but no I. 10 times 1 plus, and then the J number times the J number, 1 times 10. That's 10 plus 10, 20, done. Pretty simple, right? A little bit easier than foiling. You don't have to do all four multiplications. Just the front times the front and the last times the last. Just the F and the L of FOIL. How about that? Skip the O and the I. The O is out. So you just do the I with the I and the J with the J and drop them. So the dot product, multiply the I numbers, multiply J numbers, add the results, drop the I and the J. There we go. So you just multiply the I numbers, multiply the J numbers, add them up, and drop the I and the J. So, in other words, the answer to two vectors being multiplied is a number. That's a little bit weird. What do I mean? I mean, this arrow, what we're saying is, this arrow here times this arrow there multiplied to be 20. That's a little weird, isn't it? Why would an arrow times an arrow be a number? Well, because it's useful, it turns out. And we'll see where it's useful. But does everybody see that's kind of weird? Right? The answer is not a vector. The answer is not another arrow, is it? It's just a number. That's kind of weird. An arrow, a vector times a vector is a number in the dot product. All right. They want us to do vector V dotted with vector V. Could you do that one real quick? So dot vector V with himself. Could you do that? So I'll let you do that one real quick. Do vector V with vector V. All right, so here I'll go to a fresh screen where I can do vector V with himself. What'd you all get? Did you get the answer? 10I plus 2, that's vector V, dotted with himself. And so you multiply the 10 times the 10, plus, oh, and then the 1 times the 1. Yeah. So it's 100 plus 1, 101. Is that good? Just a number. So the dot product of two vectors is just a number. That's weird. We good? Is it all making sense? Can you see how this tool is going to be useful? No, it seems like a crazy tool, doesn't it? It's like a completely crazy tool. Do you like getting... So we're getting a new tool. That's what we're basically getting. We're getting a new tool today called the dot product. That's what we're doing. Do you like getting new tools? that's the only thing I enjoy about projects around the house. I'm the worst. My wife is very patient. I don't like them. I hate them. I'm not good at them. And so anyway, when it's time to do a project, the only thing I like about it is, I'm going to need a new tool from the store, Lowe's or Home Depot, to do this job. So recently I had to take out a tree with all these roots going everywhere. You know, trees can do that, and they can just go into your concrete, and they can pop your concrete. I was getting close to doing that. It was just destroying the yard. I got to take that thing out. I was out there with my little hand saw for a couple hours trying to cut these little roots to free up the sprinkler thing. And I thought, there's got to be something better than this. I went online. There's a Sawzall. Those are great. You ever seen those things? Yeah, about $40, $50. Not that expensive. I got the cheap thing you can get. You plug into the wall, and it just does a little saw for you. The roots are gone. It was great. So try that one. So V.W. V.W. We're doing the dot product with vector V, vector W. Minus 8i minus 5j dotted with minus 10i minus 7j. Dot those together. See the dot product. All right, so how do we do it? Minus 8 times minus 10, and then plus negative 5 times negative 7. Just the I times the I, the j times the j. Drop the I and the j. And what do you got? 80 plus 35. Is that 115? Done? It's easy enough?
Would those answers ever come out negative?
Yeah, they could. They could come out negative, yep. And then they want you to dot V with it. We're good enough. I'm going to move on to another question if you're all good with them. So, can you do this one? So, they want me to take vector U and dot it with vectors V plus W. So we learned to add vectors last time. Where do you start?
Addition.
Always start with inside the parentheses, right? So go ahead and try that one. Start in the parentheses. Add vectors V and W first off. Get that answer, and then do and then do the dot product with vector U. See what you can get there. All right, how are we doing? So V plus W. So that was just add the I with the I. That's what, 5I. And the J with the J, 5J. So that's 5I plus 5J. They're adding them. So then I'm supposed to take U dot V plus, so the U would be 3I minus J dotted with 5I plus 5J. So you don't have to show all these steps. Whatever steps you did, as long as the answer is right in the end. So the I times the I, 3 times 5 plus, and this is negative 1 times 5. What's that? 15 minus 5, 10. Do we get that okay? Adding two vectors and then dotting it with another vector. Can you do that, Clarence?
I remember from the other homework, we had like little minus signs. So let's say the dot wasn't there, we'll still act like it's going to be a dot. Like, you know how that the dot's the representation of like multiplication, right?
Right.
So let's just say it wasn't there and it just had the U right by the parentheses. It would still count as the dot, right?
No, they'd have to put it in there because it turns out, like I said, in Calc 2, there's another kind of multiplication. So they would have to specify. They'd have to put the dot or put if you went higher math, an X, which represents cross product. No, they'll put the dot. They won't just put it right next to it. They have to, because there's different kinds of multiplication.
Well, it'll come up in the next one.
Benjamin.
That's kind of something I was thinking too. Is it ambiguous to say a vector times a vector?
It is. Yeah, times, there's actually two ways of multiplying vectors. The way we're defining right now, called the dot product, and something higher up. When they get into three-dimensional, there's something called the cross product, and the two vectors actually don't make a number. You actually line them up, and it makes a vector perpendicular to the other two vectors. It's for defining planes in three-dimensional space. So that's a whole other kind of thing called the cross product. It's used a lot in physics for doing motion that goes perpendicular to two vectors. Anyway, we're not doing that. But because there's another kind, you got to specify. So we're talking about dot product here, dot product. They said, find the specified scalar. That sounds like something on Halloween night. What's a scalar? You guys know what a scalar is? It's a number. It's just such fancy talk. I don't know why they can't just say number. Why they have to give everything a name. But it just means number. Notice it's not a vector. See how our answer is just a number? It's not a vector. That's called a scalar. A scalar is just a fancy way of saying a number that's not a vector. So when you're in the vector world, you got vectors and you got plain numbers. You call those plain numbers scalars. I don't know why they don't just call them numbers. But that's what they are. So that's the verbiage. If you go into higher math, you'll see them use that.
I and the J are not X and Y.
They're not, but they're just like it. You're right. It's just another name for the same thing. That's right. So they're just emphasizing to you that when you take two arrows and you dot product them, the result is not another arrow. It's a scalar. It's a number. All right. The last of the regulars. Then we'll start doing some fancier things with not applications quite yet. Try that for u dot v. So start with the parentheses. Find the for u vector. And then dot it with the v vector. All right, so 4. How do you take, what is 4 times vector u? Vector u is the 3i minus j. So you know you just distribute, huh? It's just 12i minus 4j. That's the 4u vector. So then we take that vector, 12i minus, this is the u vector, and I'm going to dot product it with the v vector. So there's the u. Excuse me, that's the 4u vector. Dotting with the v, and what's the v vector? 5i plus j. Why'd they give us w? We never even used w in this problem, do we? Just to confuse you. So we just say, everybody good so far? I just got 4 times the u vector. Going to dot it with the v vector. So dot product. It's the I number times the I number. 12 times 5. Drop the I. Plus the j number times the j number. Drop the j. So what's that? 60 minus 4. 56. 56 is a scalar. There it is, a number. Good? That's easy enough? All seems well? Do you like this stuff? Is this fun? Pretty easy? 2 vectors. A dot product can help you find an angle between 2 vectors. A very useful thing in science and physics and engineering is being able to do that. So let's do these vectors. So I'm going to draw them. You don't have to draw them, but I just thought it'd be helpful just to see something. So vector v, what's he look like? It's 4i minus, because that means right 4 down 1, huh? 1, 2, 3, 4, down 1. So there's vector v. Vector w is right 3 up 2. Right there. So I just wanted something to look at. There's vector v and vector w. Good so far? They're arrows. What we want to know is, how big is the angle in between these vectors? This angle right here, theta. It looks a little less than 90 to me, maybe 85. And it looks close to 90. It's not meant to be 90. It's just kind of coincidentally close. Don't you think? Looks like it's pretty close to 90, maybe 85 or 80 or something. So I'm supposed to find that angle. That's what they're asking me to do. Find it. No need to draw the diagram, but I want you to see what it is they're even saying. Find that angle. Well, it turns out the dot product will help us find the angle. Like, how do you do that? You get a couple vectors. Well, turns out that here's a formula for you to write down for our test tomorrow. Cosine of theta, where theta is that angle in between, is the dot product of for any two vectors, the angle in between. The cosine of that angle is the dot product over the magnitude of vector v times the magnitude of vector w. It's kind of scribbly, sorry. We good? How are we doing? So that, now, where'd that formula come from? Just out of nowhere. No, it's in the book, the derivation. It's a little complex. I'll be glad to do it with you. Wendy would be really glad to do the derivation with you. I'd be glad to do it too. At the break or whatever. If you're interested, like, where'd that come from? I can show you where it came from. It's a little complex, so I'm not going to do it. Use up 10. It'd take at least 10 minutes of our time, or 10 to 15, to show where that came from. So anyway, I'm just going to say it's magic. It's true. It's true. The cosine of the angle in between two vectors turns out to be the dot product over the magnitudes multiplied. So, all right, let's now this. You want this on your 3x5 card for tomorrow for sure. Important theorem. There'll definitely be a question on tomorrow's test that says, "Here's a couple vectors. Tell me the angle in between them." You use that. So let's do it on this problem. How do we find the angle in between them? Well, first off, we've got to do the dot product on the top. So on the top, I'm going to write that the dot product, so V dot, or let's do it up here. V, no, I keep changing my mind. Yeah, down here, V dot W, the dot product. That's going to be, oops, kind of scribbly, so 4i minus j dotted with 3i plus 2j, which is what? 4 times 3, right? 4 times 3 minus 1. I'm just going to make that minus, I don't have room. Minus 1 times 2. Good so far? 4 times 3 minus 1 times 2. That's the numerator. Now, the denominator is supposed to be the magnitude of V times the magnitude of W. How do we find that? What's the magnitude of vector V? Yeah, remember we did that last night's homework. You guys all remember perfectly, right? I'm just joking around, but remember it's the square root of a squared plus b squared. Because look at V for example. It's how long V, or do V and W, same thing. How long is V? That's what they're asking us. Magnitude of V. That double bars mean length of. How long is vector V? Well, you can make a little right triangle here. Because vector V is down 1 over 4. So if this is 1 and this is 4, right? You with me? This is down 1 over 4. How long is the vector? Well, he's the hypotenuse of a right triangle. Right? A squared plus b squared is c squared. I could say 1 squared plus 4 squared is c squared, where this is c, the length of vector v. So how would you find it? Square root of 1 squared plus 4 squared, huh? Remember that? That's how we find the length of any vector. Because any vector's really, you could break it into his down and over. So you can say he's the hypotenuse of a right triangle. Are we good there? Is that making sense? Every vector is really the hypotenuse of a right triangle. So the length of that vector is going to be square root of a squared plus b squared. So let's do it. So vector v is going to be square root of what? 4 squared plus negative 1 squared. That's vector v, right? The two parts to v. 4 squared plus negative 1 squared. And that's multiplied by vector w. What's that? The square root of 3 squared plus 2 squared. So the length of a vector, is the square root of a squared plus b squared. So what are we going to get here? I have no idea. Square root of 17, square root of 13. So that is what? 12 minus 1, 11 over the square root of 17, square root of 13. You can multiply those together. What's 17 times 13? 221? $170, 221, yeah. How are we doing so far? Did I just lose you on that step? See where I got the 11? The top? I'm doing the top up here. 3 times 4 is 12 minus... Oh, 12 minus 2. Yeah. It's 10. I thought you all were giving me kind of a funny look. 10? Oh, it was off my screen. There it is, because my little screen shifted. There it is. Good. 12 minus 2 is 10 on the top. Square root of 221 on the bottom. Good. Now, what equals that? What's the left side? Cosine theta. Right? So I'm trying to find, so everybody good so far to this point? The cosine of theta, the angle in between the two vectors, is the dot product over the magnitudes multiplied. So I did the dot product on the top, I times I, j times j. Got 12 minus 2, 10. The bottom I did the magnitude of v, magnitude of w, root of 17 times 13, multiplied to root 221. Now, last step, want to find theta. How do I find theta? How do you get theta alone? Cosine inverse, huh?
Is that going to be radians or degrees?
Yeah, put your calculator in degrees. They want degrees on this one. I think. Yeah, answer in degrees, yeah. So cosine inverse, yeah, make sure you're in degree mode. Cosine inverse, these cancel. Theta is cosine inverse of that other side. Cosine inverse of 10 divided by...
And you want to the nearest hundred, or tenth.
Tenths, yeah, 47.7 degrees. Boy, it doesn't look like it on my picture. It looks more like... I don't know, I guess I didn't do a very good job drawing my picture. You can tell my picture is bad. See, my W comes up too far. Really, it's supposed to be over 3. It's supposed to be here. I mean, it doesn't go over far enough. And this part is supposed to be a little bit more like that. And so, yeah, it's a smaller angle. It's like, yeah, that looks a little bit better. 47 degrees. So that angle theta right there is 47.7 degrees. The angle between those two vectors. So that's something you can find. Is that good? So we can find the angle between two vectors, something very needed in physics and engineering. Okay.
That's the same kind of problem, right?
Same kind of problem. Find, so you got vector v, vector w, find the angle between them. Hey, vector v only has an I part, notice. What does that mean about its j part?
0.
0, right? We all good on that? So vector v is 2i plus 0j. and vector W is 3I plus 8J. So use that same formula. Let me write it down here. Cosine of theta is the dot product of the magnitude of V, magnitude of W, huh? So dot product over the magnitudes multiplied. So, give that a try.
Okay. Yeah, that was good. Flexible.
We good there? It's working out. So let's see. So cos of theta is the dot. Or else up here. Dot product. So V dot W. So that's going to be 2 times 3 is 6 plus 0 times 8. So that's just going to be 6. Huh? The top's going to be 6. Magnitude of V. I don't know what the magnitude of V is. It's going to be the square root. Oh, it's just going to be the square root of 2 squared plus 0 squared times the magnitude of W, 3 squared plus 8 squared. So that's going to be square root of 4, square root of 64 and 1074, 73. Is that right? Yeah, 64, 70. Yeah. Good to there? Now, the square root of 4, that's just 2, isn't it? Like that. And 2 goes into 6 3 times. So you get 3 over the root of 73. Y'all getting that? And then cosine inverse. So then cosine inverse on both sides. So cosine inverse, so theta equals.
You can have this square root of 1.
It's okay. You just can't have it in a final answer. Yeah, you can leave this square root on the bottom because that's not yet our final answer. If that was my final answer, yeah, I'd have to get rid of it. But if it's just along the way, it's fine. Just leave it, hit cosine inverse, 69.4 degrees. Y'all getting that okay? Questions I can answer? We found the angle between those two vectors. I didn't even have to draw them. We all happy about that? Is it all good?
So anytime
Honey.
J is not shown in the given, or I've...
Something's missing, it's 0.
Yeah. Okay, you don't put 1 in front of it.
Good question. Now, why? Why don't I? So vector v. Let me, rather than just like Mr. Heron says so, or what the math people say so, or whatever. Yeah, what if I said, oh, okay, I's missing, or J's missing, so I'll just make it 1. Why would that not just be a style difference, but truly wrong? Does everybody see? Why couldn't I just say, look, J's missing, V's just 2I, J's missing, so let's just make it 1. No, that's completely wrong. Why? Why is that so wrong and making it 0 is okay? That's a good thought and question. How are we doing?
It's not true, because the triangle never goes up.
Yeah. That'd be changing it, right? If you thought about what that really says, this says 2 to the right. Starting from here, go 2 to the right. Whereas this goes 2 to the right and then 1 up. Yeah, well said. I like how you're saying that one. Yeah, go 2 to the right and then 1 up. Yeah. So that's not allowed. That'd be different. Whereas if I make it 0, if I make that 0, then that's the same as the original, huh? Does that make sense? 2 to the right and none up. That's what it's actually saying. So see how that's actually the same? Is that good? Ivan actually, huh? Sorry. Ivan. All right, we good? All right, any other questions on that? Yeah. Yeah, how'd you know, Benjamin? Just remember that word?
Yeah, I think so.
Means perpendicular. It's another word for like meets at a right angle, 90 degrees, like a T. Perpendicular, orthogonal. So orthogonal just means perpendicular. 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 How are we going to know if two vectors are like 90 degrees or like an intersection? Because if you think about it, vectors can do 3 things, right? 2 vectors could be parallel. 2 vectors could be perpendicular. Here, I'll do that over here. Like one's going this way, one's perpendicular, also called orthogonal. 90 degree, they make a 90 degree angle, like, so that's like when you're going down the road. So you have streets that are parallel. You have streets like at an intersection that go in opposite directions. They're perpendicular to each other. And then what else do you have? You could have 2 streets that they're not parallel. They're a little different, but they're not meeting at 90. That's not a right angle. This would be the neither case. So we have 3 cases of what vectors can do. They can be headed in exactly the same direction or backwards. It's still parallel. Same or exactly the opposite. That's, parallel vectors. Or perpendicular, they meet at 90 degree angle here, huh? Or somewhere in between, like those weird streets, like, I don't know if you know, like Toll House Road, how it holds up, kind of goes off diagonally. And some weird streets that kind of go off at an angle. They're not exactly 90 degrees. So that'd be a neither case. All right, so that's what they're going to start asking us. How do you know, if they give you a couple vectors, if those vectors are parallel or perpendicular, called orthogonal, or somewhere in between? Well, if you think about the dot product, now, suppose the 2 vectors really are orthogonal, perpendicular, 90 degrees. What did we learn? What's that cosine theta form? It says, well, the dot product over the magnitude of the vectors multiplied, right? What if the angle is 90 degrees? Just think with me for a second. What if the angle is 90 degrees between the 2 vectors?
And that's the answer we would get when we did.
Well, then the cosine of that angle between those 2 vectors, of vector v and vector w, if they were 90 degrees, then the cosine of 90 degrees would equal the dot product over the magnitudes multiplied. Okay, great. Yeah, right. So what? Well, what is the cosine of 90 degrees? Shall we go to the unit circle? Your favorite place to go, the unit circle.
1. No, 0. Why? 0.
I hope you've all got it by the time I find the unit circle here. There it is. It's a ways back. So the unit circle, 90 degrees. Cosine sine. What's the cosine of 90 degrees? 0. Straight up. So the cosine of 90 degrees, that's, if you put in 90 here, 90 degrees, it's going to be 0. Right? So if two angles meet at a right angle, they're orthogonal, perpendicular, then the cosine of that, 90 degrees, 0. Remember the formula, the cosine is the dot product over the magnitudes multiplied. Look at this now. What does that tell you? Is that talking to you? Do we know anything about the dot product or the magnitudes from this fact? Do you know what the dot product must be? If I told you, hey, the dot product over the magnitudes is equaling 0, what does that mean? Nothing? Okay, we need to think more clearly about fractions for a minute. If I said, hey guys and gals, I'm thinking of two numbers in my head. Number on the top, divided by, and I'm dividing those two numbers in my head, and I'm getting the answer 0. I'm taking two numbers, one number divided by another number, fraction, dividing two numbers, and I'm getting an answer 0.
So the top number's got to be 0.
The top number's got to be 0. That's what that means. Do you realize that? Is that clear in your mind? The top number, the only way you're going to get a fraction to come out 0 is if the top number is 0. It's really good if that's crystal clear to me, because you'll use that in pre-calc, calc. I remember teaching calculus about 6, 7 years ago, and I put some, I hadn't even reviewed that, but I assumed they knew that. And I put it on a Calc 1 test, because it was some other fancy thing we were doing with the derivative, and it came out to where we had like a fraction equal to 0. And a bunch of them, you know, so like it was like the fraction was equal to 0. And then because of some other fancier, where it came down to this point where a fraction equaled 0. And I assumed at that point that they all knew, you grab, these are calculus students at this point, that you grab the top number and say, well, that means that top number must be 0, because the only way a fraction could be 0 is if the top number's being 0. And like half of them didn't seem to grasp that. And we're fooling around with the bottom number. I passed the exam. They're like, Mr. Heron, we didn't know how to do that one. And I'm like, what do you mean? You calculus student? You don't know when a fraction is 0? That has nothing to do with the bottom? I was kind of probably a little mean to him. I'm like, what are you doing fooling around with a bottom number? What does the bottom number have to do with a fraction being 0? Come on. Calculus students, really? I was probably a little rough on him. But I was kind of like shocked. I mean, really? Calculus students, you don't know? It never occurred to you that right? Because if the bottom of a fraction is 0, let me just be clear in case you're not clear. I wouldn't expect it. You guys should learn it at this point, and then you will know it in calculus. I would assume they would have learned that in trig or pre-calc. If the bottom of a fraction is 0, what is that? Undefined. Undefined. Good. You all know undefined. That's like infinity, huh? 0 goes into 7 an infinite amount of times, doesn't it? But if the top is 0, that's 0, huh? So the only way to make a fraction equal 0 is if the top is 0. Top is 0. So that comes up again and again. Make sure you know that. So getting back to it then. If this is a fraction, huh? And it's equaling 0. So what does that mean? That top, which is the dot product, must be 0. That's the only way this fraction is ever going to equal 0 is if the top is 0. So that means that dot product must be 0. So what have we concluded? If two vectors meet at 90 degrees, then from that little formula we just got about the cosine of the angle in between them, the theta, this is the angle in between them, equals the dot product over the magnitudes, cosine of 90 is 0. So that means the dot product must be 0. So when you have 90 degree between two vectors, their dot product must be 0. That's a quick, easy way we can test if two vectors are perpendicular or orthogonal, whatever you want to call it. If their dot product is 0. Make sense? Is that good? Is the dot product 0? Well, then the vectors are orthogonal. So that's exactly what we'll do. So let's take these two vectors. We'll say, hey, vector v and vector w, let's dot you. The I times the I, 3 times 6, plus the j times the 18 times negative 1. So I just did the I with the I, and the j with the j. It's a negative 1 there, huh? And what do we got? 18 minus 18, 0. So I just did the dot product. That's the dot product. V dot W that I just did there. And I got 0. So what does that mean about those vectors? They're orthogonal. orthogonal. Or down here they want you to say they are or are orthogonal because their dot product is 0. Ani.
So if you didn't get 0 for the top in the numerator, that means it is
Not 90 degrees. Not orthogonal.
You're still doing cosine of 90 degrees, right? Like, are you still solving it like that? If it's
No, it was. If the dot product is not 0, that must be the angle is not 90. Because it's not coming out 0.
So we don't have to put cosine theta.
No, we're not. I just use this to prove it. We're not going to need to do all this.
Oh, okay.
All we do is the dot product.
Oh, okay.
Yeah. So if the dot product comes out 0, then boom. So yeah. So the reasoning. Sometimes when I prove something, I confuse you on what you all have to actually do. You don't have to do the proof every time. I just gave the reasons behind the scenes. But all you have to do is when the dot product of two vectors is 0, they are orthogonal or perpendicular. So when the dot product is 0, they are orthogonal.
Is there like any word you can use as far as orthogonal? Or,
Perpendicular and orthogonal. That's all I can think of. It's all they're going to use in this book for sure. Yeah. So when the dot product is 0, they are orthogonal. That's how we test for perpendicular or orthogonal vectors, when the dot product is 0. So there's one use, we've seen 2 uses now, of the dot product. You could use that every day in your life when you go home this afternoon. No, I'm kidding. That's what an engineer, if you become an engineer, scientist, and those kind of things, you would use this kind of thing. Dot product is 0, they are orthogonal. Try that one. Vector V, vector W, determine whether they are orthogonal. Give you a second. Hey, they're both missing their J component, so what is J?
0.
Must be 0. Yeah. So dot them together.
so do you want me to give you that number?
My daughter's soccer team, her son is going into university high. And the freshman level coming out here, and I'll have to son. My son is 2 years old, but my son's like 10 years. So I thought he was going to take time. Presents give you the number you can talk to.
Yeah.
Unless you go watch it.
I can get more information.
Okay. Yeah, I'll just give you or them. I'll give you the. Okay, sounds good. Thanks, Wendy. There goes Wendy. She's available for tutoring. Well, not today, right? 10 to 1, right. All right. See you, Wendy. All right, so we dot product these together. It's just going to be 5 times negative 6, huh? The dot product, right? We good there? 5 V dot W, 5 times negative 6, negative 30. So it's not. The vectors are not orthogonal because their dot product is negative 30, meaning it's not 0.
They're going in the same direction.
Yeah, those are actually going the same. What are those vectors actually? Parallel. They're headed in the same direction. They're both going to the right. One's going right, one's going left, but they're both parallel, right? One of them's 5 to the right, the other is 6 to the left. Now, they didn't ask us if they were parallel, but they are. They will in a minute. Those are parallel. They're not orthogonal. They're not perpendicular. Good? Easy enough. The dot. What do you think? So let me give you a second. Try to decide if those two vectors are parallel, orthogonal, or neither. We have the 3 cases here. Anybody have any thoughts?
I see it's parallel.
Parallel. What makes you say parallel?
Because they're multiples of each other.
Yeah.
3 and -3, -6.
Yeah.
You multiply by 2.
Yeah, if you just take this times 2 times 2, you get the other one.
Right.
Vector W is just twice as big as vector V. Right? If we just double vector V, we get vector W. What does that mean? Let me show you graphically. That means V is what? Back 3, up 5. It's like there. W is like there. W is just twice as far as V. They're headed in the same direction, though, aren't they? See that? See how that is parallel? Because W is just the same as V, just double it. So basically, let me give that condition. So let me lay out. So this would be parallel. So let me lay out the game plan. So case 1, if V and W are the same, how do you say this? How about this? If V is a number times W or vice versa, then that's parallel. So if V is a number times W or vice versa, then they're parallel. That's how you know parallel. And then if V dot W equals 0, then that's orthogonal. In other words, perpendicular. And case 3, otherwise, it's neither. So that's how you do the whole test. So 2 vectors are parallel. Or 2 vectors are perpendicular, meaning at 90 degrees, or neither, kind of like that, you know? Everybody good with those 3 cases? So those are the 3 cases and how you test them. Parallel, perpendicular, neither. You kind of do that in algebra, huh? We're just doing it for vectors now. Remember in algebra how you did it? What did you use in algebra to determine parallel, perpendicular, neither? Slopes. It was all about slopes. Remember that? Anyway, so we're just using the I and the J, which is pretty much like slope. It's like rise over run if you did J over I. But anyway, I won't go there and do all that. So is that good? So that's how we test if 2 vectors are parallel, perpendicular, or neither. So we've got this tool about mastered. All right, you got that copy down. I'm going to roll on into the problem. So let's look. So we did that one. Okay, to determine if they are parallel, orthogonal, or neither. Give it a try. Use those 3 tests. Parallel, orthogonal, or neither. All right, so first off, are they parallel? Are these vectors, is one of them just a number times the other one? No, they're just like different. They're not parallel. So, no way, this is no. Are they orthogonal, perpendicular? Let's test it, huh? So, V dot, the dot product, I times I, 3 times 4 plus J times J. Minus 5 times 11. What is that? 12 minus 55 minus 43. So no, It's not orthogonal, so they're neither. Didn't come out 0, right? The dot product is supposed to be 0 if they're going to be perpendicular, because the cosine of the angle would be 90, cosine 90 is 0. Didn't happen. These are neither. Good? Easy enough? Parallel, perpendicular, neither, or parallel, orthogonal, neither. All right, let's move on. Okay, try that one. Parallel, orthogonal, or neither. So, are they parallel? No, they're not. One of them is not just 2 or 3 times the other. Let's check. So no, they're not parallel. Let's check for orthogonal. Let's do the dot product. So when you dot them, you take I times I, 5 times 7, plus j times j, which is minus 8 times 35/8. So what is that? 35. What do you do with a whole number 8 times 35/8?
Put it over 1.
Yeah, whole number interacting with a fraction. Put it over 1. Cancel. 35 minus 35, 0. There it is. 0. The dot product is orthogonal. Dot product is 0, so they are orthogonal. Good? Easy to tell? No problem? Got these tools? Bless you. A wagon pulled along level ground by exerting a force of 34 pounds on a handle that makes an angle of 60 degrees with the horizontal. How much work is done pulling the wagon 80 feet? So what they're saying is they've got, I'm gonna try to draw for you now. That's always a challenge. Okay, so we got ground here, and we've got this wagon. So far, so good. And we've got a handle. That's a little long. Okay, right here. And we got this person. It's walking along, pulling that wagon. It's as good as it gets, those stick figures and everything. All right. They're pulling that wagon, and it says that the handle, right here, the handle makes an angle of 60 degrees with the horizontal. So you got to put in the flat, horizontal. You understand what that means when they say with the horizontal, like the horizon, flat, right? So that means this here is a 60-degree angle. And they're pulling on it with a 34-pound force, and they're going to walk 80 feet. They're going to pull that wagon 80 feet. How much work is done? Now, first off, we got to talk about the definition of work. Yeah, this is physics we're talking about here. Have you studied? I'm assuming no. I mean, this is probably a good introductory point for it. If I was to take this book and lift it off the table, let's say this book weighs, I don't know, 2 pounds or something. If I was to take it, maybe it's more like 5 pounds. No, maybe it's like 2, 3. I don't know. Say it's 3 pounds. 3 pounds. If I was to lift this book up 5 feet, was that about 5 feet? About there. There's about 5 feet. So I took it from the tabletop up 5 feet, a 3-pound book, lifted up 5 feet. That's 15 foot-pounds of work. Force times distance is work. Have you ever heard of that from physics? I'm assuming no. So when I was taking trigonometry, I had not done any physics. I'm assuming you haven't had any physics yet. So this kind of gets you ready for physics. So what is work? What's the official definition of work? It's force times distance. When they are lined up in the same direction. So work is force times distance. So what is force? Force, there's a lot of ways you can measure force. Force is how hard you push on something or push on the book. So if this book weighs 3 pounds and I'm holding it steady, that means I'm pushing up with a force of 3 pounds. Because gravity is pulling down with 3 pounds. That make sense? I took a course in, I was a wannabe engineer for a while, and then I bailed out because it was too hard. At least I didn't like the hands-on stuff. Anyway, so one of the courses you take in engineering is called statics, meaning when things are static, when they're not moving, they're not dynamic, they're not in motion. They're standing still. Like this book right now is standing still, which means what? Which means all the forces acting upon this book must be balanced, or that book would be moving. You with me? So what forces are acting on that book? Well, I'm pushing up on the book right now. If I don't push up, the book falls. Right? So I'm pushing up on the book.
Gravity's pushing.
And gravity's pulling it down. And we're balanced right now. I'm pushing up. Now, if I'm going more than gravity, then the book goes up. If gravity is stronger than me, then the book goes down. But if we're equal, if something's not moving, something's static, then the forces are in balance, aren't they? So me and gravity are balanced right now. The book, it's pulling down with 3 pounds of force. I'm pushing up with 3 pounds of force. No work is being done. But once motion starts, once you take a force over a distance, physics made that up and called that work. It's made it up, like all math. They thought, hey, things happen in the real world where forces are exerted over a distance. We gotta make something up for that. We'll call it work. So if I grab this book off the tabletop and lift it up 5 feet, then that would be 5 feet distance. The force I said was 3 pounds. That's how much it takes to lift that book up. Multiply those. That would be 15 what we call foot-pounds. Sounds like a weird unit, huh? 15 foot-pounds of work. So when I lift up this book 5 feet, that's 15 foot-pounds of work. Now, work is how you know how much if you're on the treadmill, they can convert that to calories. You know how they can give you your calorie count? Well, the machine's basically counting how much force you're putting on those pedals over how much distance, repeatedly, force times distance, getting work and calculating that over to calories in energy spent. So if you have an engine and you want the car to move you down the road or the lawnmower or the whatever, the electricity coming out of the wall is going to accomplish moving something or rotating something. It's a force over a distance calculates total work done. That's what physics uses this for. That's how we figure out how much energy things, what energy can get what done in the real world. So let's get back to this problem. So everybody with me on this definition. What is work in physics? Force times distance when they are lined up. Was I lined up? When I was picking that book off the table and lifting it straight up, what direction was the book moving? Well, straight up. That was the movement. The distance moved straight up. What direction was my force pushing? Was I pushing sideways on the book? If I pushed sideways, the book would just fly right out of my hand. I wasn't pushing sideways. I was pushing straight up, wasn't I? So my force was straight up, and the book was straight up. They were lined up. Both my force direction and the movement direction were lined up, both going straight up. So I could just go 3 times 5. Come back over here. Is that what's happening here? Can I just take, look, 34 pounds of force? That's how hard the person's pulling on that wagon. They're pulling with a 34-pound force, right? Exerting a force of 34 pounds. And, right, so let me write that right here. Force, 34 pounds. And they're moving the wagon. How much is done in pulling the wagon? The distance for the wagon is 80 feet. Should I just take 34 times 80, multiply them, and we get the work done?
No, I think there's something to do with the angle of the handle.
But why? Because they gave me an angle. It's got to be used. So why can't I? Why can't I just multiply 34 times 8? Isn't that what we just said? Work is force times distance as long as they're lined up. Right? Yeah.
Is it because
I think.
the
Not
horizontal
long.
and the 34 pounds aren't going in the same direction?
Ah. Yeah, are those lined up? Let's be super clear. What's the direction of the movement?
Right.
Straight right. Just straight right, right? The wagon's not floating in the air. The wagon's going to move straight to the... So there's the distance vector. See where vectors are coming in? That's the distance vector. It's moving straight to right. Now, where's the force vector? Where's the force vector on that wagon? It's right there. Isn't that the force vector? The person's pulling on that handle.
If the handle was straight, then it would be.
Yeah. If they would stoop down, right? They would just stoop down and pull that wagon so that handle was level, then I could just multiply those numbers. Right? Look how they help us out. Stoop down. I can just multiply the numbers. Makes the math easier. Right? Everybody see the deal. Because they're not stooped down and that handle's not level, if they would just stoop down and make that handle level, then the force and the distance would be in the same direction. I could just multiply those numbers. That'd be great. But they're not. They're pulling at an angle of 60 degrees up to the right. The force is up to the right. The distance vector is straight to the right. Those are not lined up. And lined up means parallel. Exactly lined up. Like me pushing the book, me lifting the book. My force vector is straight up. My movement vector is straight up. They're parallel. Perfectly lined up, so I can just multiply. But that's not what's happening here. They're not perfectly lined up, are they? So I may not just multiply force times distance. That's not going to be it. What are we going to do?
Is it cosine? Well, if that's the angle, you would want to find the thing that's adjacent to it, right? Because it represents the horizontal, like.
Nice, Clarence. I like how you're thinking. Yeah. So you see what Clarence is saying? Clarence is saying, well, okay, yeah, this force, it's a vector. This force vector. Can't we find the part of the force that's sideways and the part of the force that's vertical? Remember how last section we talked about taking a force? Didn't we have like a tugboat problem or something like that? And you had forces in a couple directions. Remember those? Yeah, so Clarence is talking about, can't we take the force that's sideways and the force that's vertical and break it up and do that kind of thing? Yeah, that's exactly it. Yeah. How could we get that force that's sideways? If somebody's pulling up to the right, what that means is part of their pull is to the right and part of their pull is up. That's what it means to pull upright. Part right, part up. So what part's right? Because the part that's right is in line with the distance, and then I can multiply those numbers. Does that make sense? So how do I find the part that's to the right? Clarence, you were saying.
Cosine?
Cosine, remember? Remember how we learned? Anything x is cosine, anything y is sine. So what is the part of the force that is straight to the right? It's going to be the 34 pound magnitude. Remember magnitude times cosine of the angle. Remember that? And the part that goes up is magnitude sine of the angle. That's the J component. This is the I component. Remember that? Remember when we turned vectors from the magnitude is 34. That's the total amount of force being applied at a 60-degree angle. Remember in last night's homework or over the weekend or whenever you did it, that we went from magnitude and angle to IJ? Remember how we did it? What Clarence is saying, magnitude cosine of the angle for I, magnitude sine of the angle for J. That's how we turned it from a diagonal thing to an IJ kind of thing. And why is that so valuable? Because now we can take this part, which is lined up with the distance, and now we can multiply those to get our answer. That would tell us the work done. Having said all that, let me give you the clean, because that's it. That is the right answer. But let me give it to you in a really clean package that'll always work. Here's what it is. Force, how you determine work. I wrote somewhere part of the definition. Let me give the official definition now. Work Remember I wrote it force times distance. What did I write?
Force times distance.
It's force times distance when they're lined up in the same direction. Well, what if they're not? Like here. We got the wagon force is not, I mean, most of the time your force is not exactly in the same direction as your movement. What do? Work is force dot product distance. And that's not just when they're lined up. That's always. Always. Am I making some sense? This is where the tool of dot product comes in to help us. Force dot distance. That dot right there is the dot product. So you got to make force a vector and distance a vector, and then you just dot product them, and that takes care of the line up, not line up, whatever. That takes care of the whole thing. And you don't have to worry about lining them up yourself. There it is. There's the big use of the dot product. Force dot distance. So let's do it. So what's the force vector? Well, we've actually got the force vector, don't we? The force vector is 34 cosine 60i. Clarence got it for us. Plus 34 sine 60j. That is the force vector, isn't it? Everybody with me on that? Remember that was from last night's homework. When you have any kind of vector at an angle, diagonal angle like that, any angle, doesn't matter, then you break it into I and j by taking the magnitude, the total length of it, 34, cosine of the angle I, sine of the angle j. So I just took that force of 34 pounds at 60 degrees and made it 34 cos theta I, 34 sine theta j. That's the force vector in terms of I and j. What's the distance vector? The distance is 80 feet. 80 feet what? I, j, some combination thereof. 80i. Pure I. Look at distance. Is it going up at all? No, it's pure to the right, isn't it? That wagon is moving purely to the right. So when they say 80 feet, that's 80i, isn't it? Is that good? So you see how I made the force and the movement, the distance, into vectors. Vectors. So I made the force into I and j, right and up components, and the distance just was a right component, 80i. Right? They said it, it just moves on level ground, 80i. And so now I can do the dot product of the two, because that's the definition of work. It's the force dotted with the distance. So here we go. So the force, well, I don't know if I have room. Can I go to a fresh screen? So let's do that. So the force dotted. What was the force vector? 34 cos. Okay, so there it is. 34 cos 60 degrees I plus 34 sine 60 degree j dotted with the distance, which was just 80i, right? Wasn't it? 80i. And if you want, you can put a plus 0j if you want. It's not really needed. It's your option. So the force vector, the distance vector. So this is what work will equal. So work will equal the force vector dot the distance vector. We ready? So how do we do it? How do we do dot product? We got this tool in our hand now. We know how to use the Sawzall. You know what you're doing? Clarence.
How was the 80? I was right.
Yeah, they told us that the wagon moved 80 feet on level ground. So that means 80 feet pure sideways, 80i. Is that good? See why the distance, the movement is 80i? It's 80. The person is pulling diagonally, but the wagon is moving flat 80 feet. So we're saying how much work did that person get done? They were pulling at 34 pounds of force, and they moved that wagon level ground 80 feet. How much work would that, if that was a motor, how much energy did that take? How much gasoline, whatever. You got to determine the work that something does. This is how engineers, physicists figure out what motors and engines can put out as they calculate work. So here we go. So the I times the I. So it's 34 cos 60 times 80 plus 34 sine 60 times 0. J with J, that won't do anything. So it's really just that, isn't it? It's really just 34 cos 60 times 80. And I'm getting 1360 foot-pounds. I don't know if you know the abbreviation for pounds, LBS, foot-pounds. I'll just write it out longhand. 1360 foot-pounds. That's how much work that person did in pulling that wagon. 1,360 foot-pounds of work. So see how what Clarence was saying ends up being the answer? Right? Remember how he was saying, well, can't you do the part that's lined up? That's exactly what it ended up being, right? 34 cos 60 times the 80. See how the dot product just handled that for us automatically? Without thinking too hard? Just do the dot product. Well, however the vectors are, doesn't matter if they're lined up or not. Just do the dot product, and it'll give you the work. It'll handle the lining up for you. Is that good? All is well? Questions on that? Is that good? See how to use that dot product tool? All right, let's try another one of the same kind of problem.
I was going to ask that. What incline's going to mess with the whole thing?
Yeah, yeah. This is where the dot product will make it not too bad. So force of 80 pounds on a rope is used to pull a box up a ramp inclined at 10 degrees from the horizontal. So this time we're not going on level ground, are we?
No.
So in other words, our movement vector is not just going to be I. It's not just moving right, it's moving right and up. The movement vector will have an I and a J, won't it? Does that make sense? The figure shows that the rope forms an angle of 33 degrees with the horizontal, so that's the force vector. How much work is done in pulling the box 22 feet along the ramp? So basically the whole work of the problem, it's almost like a pun there, the difficulty of the problem is to find the force vector and the distance vector, or the movement vector. So can you find the force vector first off? Let's start with that one. So here's the force. The force is 80 pounds at an angle of 33 degrees with the horizontal. So that means it's going to have an I and a J component. Isn't it? Why don't I just pull it over here? Say force. I'll draw it up here. So the force of 80 pounds at an angle of 33 degrees with the horizontal is going to have an I and a J component. It's going to have a sideways and an up, isn't it? The person, the rope is being pulled up to the right. Right? That little box sliding on the incline there is being pulled up to the right at an angle of 33 degrees to the horizontal, which means to the flat. They're going to say that all the time, to the horizontal. 33 degrees to the horizontal, to the flat. And so can we find the sideways component and the vertical component of that pull? What's it going to be? 80 cos 33I, 80 sine 33J. Good so far? The sideways is always cosine. Remember, because cosine is always x. Remember on the unit circle? See how that ties together? We talked about that last week. that the sideways is always x, is always cosine, is always I. So x, I, cosine always go sideways, don't they? And the vertical is always sine. Does everybody remember that? So whenever you have a vector at an angle, the I is always cosine, the J is always sine. Bless you. Make sense on that? Remember that? That good? So I've got the force vector. What's the force vector? It is 80 cosine 33I plus 80 sine 33J. There it is. That's the force vector. Now we need the distance vector, the movement vector.
Would it be 22 cosine 10?
Exactly. Yeah, because how far does it move? They tell us that the box moves 22 feet. So this ramp, the box is going to move 22 feet along that ramp. Now we're doing the distance or the movement vector. So they're both vectors because they both have a sideways component and a vertical component. They're both diagonal. But they're not exactly lined up, are they? The force is pulling up more. That's at 33 degrees. The ramp is only at 10 degrees. Everybody tracking with me? It's making sense? So what's the distance vector? Well, the total distance is 22 feet along the ramp. So that's going to be 22 cosine of the angle, 10 degrees I, plus 22 sine of the 10 degree angle, J. How are we doing? Is this making sense? So whenever you have any vector at an angle, the x, the I is cosine, the y is sine. I mean, the j is sine. And now what do we get? What do we do to get how much work? How much work is done in dragging that box 22 feet up that ramp at that force angle? You dot product them. That's the great ability of the tool dot product. It can calculate work. So the work done is F dot, d the dot product. So I take 80 cos 33 times 20, so you just multiply those together, just the I times the I. So 80 cos 33 degrees times 22 cos 10 degrees plus the J times the J. 80 sine 33 times 22 sine 10. And add those up. Just hit the buttons on your calculator. Everybody see what I did there? I just multiplied the I with the I, the J with the J, dropped the I's and J's, and add them up. So let's see what we get. I'm getting 1620. 1620. How far do I? Nearest foot pounds. So 1620 foot pounds. 1,620 foot pounds of work is done.
I like considered a lot of work.
I don't know what a lot is. And the numbers come out big, which kind of mean that. Those are big numbers, yeah. All depends on the units and stuff. Oh, yeah, there it is.
33 feet. It's the same problem I got.
Is that good? Is that making sense? Are you guys all getting comfortable with this kind of stuff? You just convert the force and the movement distance into vectors, and then you do the dot product.
Right. Oh, 21. Mine was off by 1 foot.
All right, you ready for the next one? Is that okay? I was going to move ahead if you're good. All right. Last time. So you might remember. Force is given by, there it is, they're just handing you the force vector. Silver platter. The force vector is 5I plus 2J. So no, we don't need to work hard for that at all. They're just handing me the force vector straight out. There it is. There's the force vector. It's 5 to the right, 2 up. That's the force vector. But the distance, the movement, moves an object along a straight line from negative, it moves from negative 4, 4 to 4, 7. So the movement vector is a little more tricky. I got to come up with a movement vector, the distance vector, and then when I do, I just do the dot product and we're done. So how do I get that movement vector? Anybody remember from last time? We did some of these where we had a couple points. We need the I and the J, don't we? We need the I and the J.
The second x minus the first
Yeah. It's going to be x2 minus x1I plus y2 minus y1 J. Yeah, if you want the sideways movement, you have to subtract the two x values. And if you want the vertical movement, you got to subtract the two y values, right? Because the difference in x values is going to give you the sideways, isn't it? How far apart those x's are? Is that making sense? I don't want that to be just a formula I wrote up there for you. I'm a little concerned that I didn't see a lot of people remembering it, which makes me think that I wasn't making good sense of it for you. Think about it. Rather than just go ahead. This is minus 4, 4. 1, 2, 3, 4. 1, 2, 3, 4. There's that point. Minus 4, 4. Right? Which means it's back 4. It's up 4. Right? This is the x value, the y value. Right? The other point is 4, 7. 1, 2, 3, 4. 4, 5, 6, 7. Up here it's 7. So this is 4, 7. That's the x. That's the y. So over 4. Up 7. So I want to go from this point, I want a vector going, there's my vector, there's the distance vector. The object we're moving went from minus 4, 4 to over 4 up 7. There's the movement. That's how that's the movement vector. That's how the object moved. It moved from the spot minus 4, 4 to the spot 4, 7. Didn't it? Well, how do you find out its I and J components? How do you find out how far to the right it moved? That's the I. And how far up it moved? Its I is how far sideways. Its J is how far up it moved. How do you find how far it moved sideways? You got to subtract these two x values, don't you? You got to take the second x value minus the first x value to get the sideways movement. It's going to be 8, isn't it? From negative 4 to 0 is 4, and all the way to positive 4 is another 4, 8. Right? And how do you get the J, the vertical? Well, again, it's going to be the y2 value up here, the 7, minus the 4, huh? See how we got the difference of y values? J and the difference of x values is your I? Does that formula make a little more sense now? So that's it. So you don't have to do all this drawing stuff. This was not needed. I was just trying to make it make sense for you. All you have to do is difference of x values I, difference of y values J. So here we go. So it's going to be, because this is x1, y1, x2, y2, right? This is the first points, x and y value. That's the second points, x and y value. So difference of x values, x2 minus x1, 4 minus negative 4. That's going to be 8i, right? Because the double negative is going to add. Is that good? plus the difference of y values, 7 minus 4, j, which is 3j. So that's the movement or distance vector. Right 8 up 3, isn't it? This vector, which moves diagonally from minus 4, 4 to 4, 7, moves right 8 and up 3, doesn't it? 8i, 3j. Right 8 up 3 in that diagonal movement between those 2 points. Does everybody see that? So the sideways is just the difference of x's. That's the I. And the vertical is just the difference of y's. That's the j. 8i plus 3j. That's the distance that particle moved, whatever we're moving here. All right, so we're ready to answer this question now. I've used up all the space, though. I guess we're done. Oh, no. So we got to do the work, which is dot product. Right. So let's do that. I'm going to erase this graph stuff. Put it in over here. So the work now is the force vector dotted with the distance vector. So the force vector, 5i plus 2j, dotted with the distance vector, which is 8i plus 3j. So the force vector dotted with the distance vector. So the I times the I, 5 times 8 plus 2 times 3, 40 plus 6, 46. There it is. The total work done, 46 foot-pounds. All right, how are we doing? This making sense? So it's just force vector, distance vector, dot product. And if they give you 2 points, you take the difference of x's for your I and the difference of y's for your j. They're going to give you both those in the next question. You ready? You good with that one? Okay. A force of 4 pounds acts in the direction 45 to the horizontal. So they're giving you the angle thing. Remember what we do with that? Let me write the key facts up there for you. So force, 4 pounds at 45 degrees. And then the thing moves. It moves from 4, 6 to 5, 10. So you got the information you need for a force vector in terms of an angle and a movement vector in terms of 2 points. So do both things we've learned and then do the dot product. Find the force vector, find the movement vector, and dot them. So how do we find the force vector? What do we do when there's an angle? Cosine is for the I, sine is for the j. You got to put the number in front, huh? So 4 cosine 45 degrees I plus 4 sine 45 degrees j. Everybody good so far? So there's the force vector. Now write the movement vector. dot them together. The distance vector is the difference of x values. So this is x1, y1, x2, y2. So it's 5 minus 4I plus 10 minus 6j. So the distance vector is 1I plus 4j. Is that good? So we've got the force vector, we've got the distance vector. Now dot them, right? It's getting routine, easy. So the work done, force vector dotted with the distance vector. So I'm going to take the I times the I. So that'll be 4 cosine 45 degrees times 1 plus the j for sine 45 degrees times 4. So there it is. Just add them up. Drop the I and the j. So 4 cosine 45 plus 4. It's going to be 16. F1 is 4, 16. Sine 45. I'm getting 14 and nearest hundredth, so 14.14 foot-pounds of work on that thing. And moving that object. That's the work done. So that's how engineers calculate work done by various motors and engines and electrical powered things and battery powered things, or even human beings. Work done and making something move with a force.
It's just easier to write.
Questions on that one?
So that you can